Hi boys and girls, this video comprises the lecture for section 7.4 starting on page 476, and we're going to be discussing arc length. Now this section also contains area of a surface of revolution, but that topic is not necessary for the BC exam. However, arc length is, so we're going to talk about that here and not worry about surfaces of revolution for now. Definite integrals can be used to find arc lengths of curves. An arc is a segment of a curve, the length of which can be approximated by straight line segments whose lengths are given by the distance formula. Adding up the lengths of an infinite number of successively smaller line segments requires an integral, which we happen to have. I'll demonstrate how this is going to work on the next slide, but first let's go ahead and have what our definition of arc length is. We need to have a function that is a smooth curve, continuous and unbroken on a specific interval. The arc length between a and b will be given by the integral from a to b of the square root of 1 plus the derivative of the function squared dx. Of course, if the equation is written in terms of y, we're going to have endpoints of integration on the y-axis instead. The function in terms of y, we would have that derivative squared plus 1 and then take the square root. So we need to memorize this for sure. Don't really need to memorize it twice, but you'll need to be able to use it whether the function's given to you in terms of x or y. Now on this slide, I've taken a couple of screenshots from your book to sort of demonstrate what's about to happen here. Notice in this first little graph, we have the arc length that we're talking about. This is some function, looks like some sort of parabola, and from a to b, we wonder what the actual length of the curve is from a to b. Now, this is not the distance from A to B straight line or anything like that. It means the actual distance along the curve from A to B. Now, think about how you would find this distance mathematically without calculus. There really isn't a way to do this unless we have a straight line and we could, and the endpoints of that straight line, we could use the distance formula. Or if it was a circle, we could find we could use the circumference of a circle using the radius, etc. But just some amorphous curve to ask to find what is the length of the segment from start to end, we don't really have a way mathematically to do that until now. Now, I suppose non-mathematically, I could take a string and lay it along the curve from A to B and then measure the string, but we would rather have a mathematical way of doing this in order to find the length of that arc, and of course we do. Now, of course, the integral is going to be summing up a bunch of little line segment lengths that we're going to find, and I've demonstrated that here by putting 5 data points on here. Connecting them all gives me 4 line segments. Using the distance formula, I could find the length of each of these segments, add them up. I would have an approximation of the length of that arc. And of course, if I used more data points closer together, smaller segments, using the distance formula, found the distance of each of those segments and added them up, I would have an even better approximation of the arc length. Of course, the smaller the segment, the better the approximation would be. The idea, of course, will be that we get a segment of virtual length, that we're going to have every data point along this curve represented. This is why we need an integral, and adding up the sums of those line segments with virtual length will give us the actual arc length of the curve. It's kind of a miracle every time. Now I want to remind you of how we find the length of a segment. Here is the point x1, y1, x2, y2. Notice that that forms the hypotenuse of a right triangle. And if we know the length of A and B of the right triangle, we can find the length of C. And since C is representing the length of the segment that we want, that's what this will help us do. Subtracting the y values gives us the length of A or B, whichever you want to call it. Subtracting the x values gives us the length of the other side. Squaring both of those, adding them together, and taking the square root will give us C. Remember, a squared plus b squared equals c squared, but if we're solving for c, we would take the square root of a squared plus b squared. And of course, that's where the distance formula comes from. Now, I also wanted to let you know that from the distance formula to the arc length formula, that is derived in depth for you on page 476 if you want to follow through to see how the distance formula becomes the arc length formula. Whoops, I did the wrong thing here. Becomes the arc length formula. There is a connection, and as I said on page 476, you can see how that works. But we're going to go to example 2 on page 478. We have a function, here it is, we're interested in the arc length from 1/2 to 2. And remember that as you memorize this formula, the function, you have to take the derivative of it, you have to square that, add it to 1, and then take the square root of it. So I'm going to do some of this work in getting the integrand ready off to the side. We'll start with the fact that this can be rewritten as y equals 1/6 x cubed plus 1/2 x to the negative 1, which means y prime is equal to 1/2 x squared minus 1/2 x to the negative 2, which can be written as 1, or we'll just write this as x squared over 2 minus 1 over 2 x squared. Now notice this derivative is squared in the integrand, so I'm going to go ahead and do that here. X squared over 2 minus 1 over 2x squared. You have to write it down twice and FOIL it, of course. And in doing so, I'm going to get x to the 4th over 4, and then this is going to become minus 1/4, minus 1/4 again, and then plus 1 over 4 x to the 4th. And now, if you'll notice in the formula that after squaring the derivative, I have to add it to 1, so I'm going to do that here. This is going to give me x to the 4th over 4, and then negative 1/4 and negative 1/4 is negative 1/2, plus 1 is positive 1/2, and then I end up with plus 1 over 4 x to the 4th. Now I'm going to factor out the positive 1/4 because often when you have something under a radical, you want to factor out something that's a perfect square to make things a little simpler. This happens a lot with arc length. If I factor out that 1/4, I'm left with x to the 4th plus 2 plus 1 over x to the 4th. Now remember with the 2 here, 1/2 divided by 1/4 is the same as 1/2 times 4 over 1, which is a 2. Of course, 1/4 times 2 does give you 1/2, as you can imagine. So now once I've taken out this 1/4, believe it or not, this factors into x squared plus 1 over x squared quantity squared. Since these are both perfect squares, now that I put those under the radical part of the formula, I end up with 1/2 quantity x squared plus 1 over x squared. Now let's put it into the integral dx and get ready to integrate from, what are our endpoints of integration? 1/2 to 2. Let me take out the 1/2 and rewrite this a little bit as 1/2 to 2 x squared plus x to the negative 2 quantity dx, and then this becomes 1/2 times, we are going to have 1/3 x cubed, and then minus, when we add 1 and divide by 1, we end up with x to the negative 1 from 1/2 to 2. Now, it's really easier, I think, to plug in endpoints of integration when you have this written this way rather than the other way. So I'm just going to rewrite it like this. And then once you plug in 2 here, get 8/3 minus 1/2. 1/2 here becomes 1 over 24. That's a cubed, by the way. 1 over 24 minus 2, and then multiply all of that times 1/2. You get 33 over 16 as your arc length. That was fun, wasn't it? Let's do another one. This is example 3 on page 478. And for this example, we're going to take a function and write it in terms of y and use the arc length formula. So the first thing I'm going to do is rewrite this, solving for x, by taking the square root of both sides. So I'm going to end up with x equals, of course, plus or minus, this becomes the square root of y minus 1 quantity cubed. Now, since I have the top half of the curve here that I'm dealing with, it's the positive portion. Let's rewrite this as y minus 1 to the 3/2 power, because taking the square root is like the denominator of the fractional exponent. Let's take the derivative now. X prime is equal to 3/2 y minus 1 to the 1/2 power. And then when I square that, because remember the next part of this is to square it, I'm going to have 3/2 y minus 1 to the 1/2 power squared ends up giving me, squaring 3/2 gives me 9/4, but then 1/2 times 2 now just gives me y minus 1. Let's distribute this. This becomes 9/4 y minus 9/4, because of course we have to add 1 now. That's the next part of setting up the argument of the square root function. When we add 1, we end up with 9/4 y, and then this becomes minus 5/4. Let's go ahead and factor out the 1/4 again. We end up with 1/4, and then this becomes 9y minus 5. Let's put that under the radical. And then we can take the square root of 1/4, which is 1/2. And 9y minus 5 isn't going to come out of the radical, but there we have the setup for our integrand. So now we can go ahead and put this in the integrand. We know that in this case, since everything is in terms of y, we're integrating with respect to endpoints on the y-axis from 1 to 5. And so now if I take the 1/2 outside, and I rewrite this as 9y minus 5 to the 1/2 power, we can sort of do a u to u substitution to set this up. If u is equal to 9y minus 5, du, of course, is equal to 9 dy. So if I put a 9 here and a 1/9 on the outside, essentially I have the integral of u to the 1/2 power. The 9 and the dy that should be here, the 9 and the dy are the du, and of course 9y minus 5 is u. Well, the integral of u to the 1/2 is 2/3 u to the 3/2. So this becomes 1/18 when I integrate this times 2/3 our u, which was 9y minus 5 to the 3/2 power, from from 1, hey, that's supposed to go away, from 1 to 5. Simplifying this a bit further, I get 1/27, 9y minus 5 to the 3/2 power, from 1 to 5. When you put 5 in here, you get 40 to the 3/2 power. When you put 1 in here, you get 4 to the 3/2 power. Subtracting those two, multiplying by 1/27 gives you approximately 9.073. All right, I'm going to try to go through one more example. Example 4 on page 479. Now we have, here's our curve and here's our arc length, and we're integrating from 0 to pi/4. So first of all, y is equal to the natural log of cosine of x. So let's take the derivative. Oops, need that equal sign. Y prime is equal to 1 over cosine x times the derivative of cosine, which is negative sine x. Of course, this is negative tan x. And remember, we have to square that derivative. So now let's square it. We're going to get tan squared x, then add 1 to it. Turns out that this whole thing is secant squared x. Isn't that amazing? Now when we take the square root of secant squared x, we end up with secant x. Let's go ahead and set up our integral now with our simplified integrand, which is simply secant x dx, and we're integrating from 0 to pi/4. Now, integrating secant is has that unusual method where you multiply by the natural log of secant x plus tan x over, or no, multiply by secant x plus tan x over secant x plus tan x, and it ends up being the natural log of, if nothing else, just memorize the integral of secant x, tan x, from 0 to pi/4. And when you plug these lovely values in and work it out, you get approximately 0.881. Of course, these examples are in your book, so if you want to go follow along in a bit more detail, you can do so. And that's it. I have one more integral for you. Yes, I hope that doesn't depress you, but it is a true statement. And your homework is page 482, 3 through 24, multiples of 3. That's it.